All right, welcome to today's Explainer. Today we're unpacking what is honestly one of the most elegantly designed systems in the physical world, parallel circuits. Instead of just kind of wondering how this massive, complex web of electronics actually powers your everyday life, we are going to break down the exact physics of having multiple electrical paths. We'll explore the mathematical realities and, frankly, the engineering brilliance that makes our entire modern electrical grid possible. Let's get right into it.
Have you ever just stopped and looked around a standard room and thought about the electrical layout? Think about it. When one overhead fluorescent tube dies, the whole room doesn't suddenly go dark, right? If you yank your phone charger out of the wall, your laptop doesn't instantly shut down. This localized failure, where one thing breaks but there's no systemic collapse, that is the precise engineering triumph of parallel wiring. It isn't magic. It's a very deliberate, highly efficient architectural choice.
So, what exactly is happening behind the drywall? By definition, a parallel circuit connects its components in branches. The absolutely crucial part here is that it offers multiple paths for current to flow. Now, compare that to a series circuit, where electrons are basically forced to march in the strict single-file line through every single component. A parallel architecture creates forks in the road. The electrical current literally gets to choose its route, establishing these totally independent lanes of power, all coming from one single source.
Okay, let's dive into this visually. If we look at a classic setup with a battery and three distinct branches, you'll immediately notice this ladder-like architecture. The main line coming from the source hits a junction, and that allows the current to split independently down through the first bulb, or the second, or the third. The top wire connects all the top terminals together, while the bottom wire connects all the bottom terminals straight back to the source. It's a design that guarantees every single path remains completely autonomous.
Now, there are two absolute golden rules governing this system. First up, voltage is constant. Every single branch gets the full, unadulterated push of the source voltage. If the battery is putting out a certain voltage, every path feels that exact same pressure. No watering it down. Second rule, current adds up. The total current leading that battery is just the sum of the current flowing through each individual path. They split off from the source, do their thing, and rejoin before heading back home.
Let's put some real numbers to this to see how it works practically. Say we connect three 85-ohm light bulbs to a 48-volt source. Because of our constant voltage rule, every single one of those bulbs experiences that full 48-volt push, completely independent of the other two. The electrical potential doesn't get diluted, and it doesn't get split between the branches. It is 100% replicated across each and every path.
Now, what's really interesting about this setup is how we calculate total resistance. Because we have multiple paths, we have to use inverse fractions. I know, fractions, but hear me out. Instead of just adding up resistance numbers like you would in a series circuit, adding a new branch in parallel is kind of like opening up a brand new lane on a congested highway. It actually makes it easier for the overall traffic to flow, which drops the total resistance of the whole system. The math using those inverses perfectly reflects that easing of the current's journey.
When you actually run that inverse equation for our 385-ohm bulbs, boom! Our total resistance drops dramatically to just 28.57 ohms. That's way lower than the 85 ohms of any single bulb. And because that overall resistance is so much lower, the current can flow much more freely. So while each individual bulb draws about 0.565 amps, the total current leaving the battery is the sum of all three. That gives us 1.70 amps flowing through the entire system.
But hold on. What happens when the branches aren't perfectly identical? Let's say we introduce a 9-volt source to three drastically different resistors. We're talking a 10,000 ohm, a 2,000 ohm, and a 1,000 ohm resistor. Suddenly, these available paths offer completely different levels of difficulty for the electrical flow. We've essentially set up an environment where the current has to distribute itself unevenly, entirely based on finding the path of least resistance. Let's move along and see how this builds. Breaking down the math for this asymmetrical circuit proves something fundamental. Electricity is inherently lazy. It behaves just like water. While that 9-volt push remains exactly the same across all three branches, that massive 10,000 ohm resistor only draws a microscopic fraction of an amp. Meanwhile, the easier path, the 1,000 ohm resistor, draws significantly more. The lower resistance paths will always dominate the current draw, which allows the whole system to naturally balance the electrical flow based on the friction in each branch.
So the crucial point here is what happens when we sum it all up. Summing those individual currents gives a total draw of 0.015 amps leaving the source. And here is the truly mind-blowing part. The total resistance of this entire circuit comes out to just 625 ohms. Think about that for a second. Even with a massive 10,000 ohm roadblock sitting on one branch, just the availability of easier alternative paths reduces the overall friction of the system to a number well below the value of the absolute smallest resistor. Multiple paths fundamentally reduce systemic resistance.
If we expand this logic to a simulation of 4 distinct bulbs, it visually proves exactly what we just calculated mathematically. Basically, the more parallel paths you add, the more overall current gets drawn from the source. Your battery is forced to supply the sum total of whatever each new branch is demanding, which means, theoretically, if you had infinite branches, you would need infinite current. It perfectly illustrates this direct, unavoidable relationship between the size of a network and its total power draw. Stepping back for a second, you can really start to see why engineers absolutely love this architecture. It offers massive advantages. It gives you independent functioning. You can switch off one component without killing the rest. It guarantees consistent brightness across all your bulbs, because remember, the voltage remains constant. And most importantly, it gives us built-in redundancy. If one path fails or a part breaks, the current just bypasses it and routes through the remaining branches. The grid survives intact. And look, this isn't just chalkboard physics. It is quite literally the invisible infrastructure of your home. Every single time you plug in a toaster or a vacuum, you are adding a brand new parallel branch to your house's grid. This is what allows your refrigerator, your lights, and your TV to all operate completely independently while pulling from the exact same voltage source. Parallel design is the whole reason modern domestic life can function smoothly with dozens of appliances running at the same time.
And this brilliantly illustrates the flip side, right? The limitations. This system requires significantly more complex wiring than just a simple series loop. Plus, because every added load increases the total current, if you plug too many high-power appliances into one set of parallel outlets, you're going to draw massive amperage. That risk, overloading and overheating the wires, is exactly why we have circuit breakers and fuses. They exist to literally sever the main line and protect the system before a fire can start.
So, I want you to look around your room right now. Consider the lights, the chargers, the appliances just silently standing by. Think about the massive network of hidden, parallel circuits branching through the walls around you, effortlessly dividing voltage and summoning current to safely power your daily life. The next time you flip a switch and just a single light illuminates, you'll know the elegant, invisible physics that makes that independence possible. Keep observing the hidden systems around you, and I'll catch you in the next explainer.